Hi guys, this is Dr. G here. In this video, we are going to continue our discussion on alkenes. We already talked about the fundamentals that are associated with alkenes, and also we talked about the mechanism of electrophilic addition of alkenes, and also we talked about the synthesis of alkenes in a previous video. And in this short video we are going to talk about two very important reactions that alkenes show, which is basically halogenation and halohydrin formation. Halogenation reaction and halohydrin formation reaction. So uh, the first reaction that we are going to talk about today is halogenation reaction for alkenes, and this can be done through a treatment with bromine or chlorine. Okay, so you can treat alkenes with either bromines or chlorines to halogenate the the alkene. And the important thing about this reaction is that you don't have to worry about the Markovnikov rule, which basically is important for electrophilic addition reactions of alkenes. But in here, you don't have to worry about the Markovnikov rule. Why? Because both atoms that are going to be attached to the sp2 hybridized carbons are going to be a halogen. So therefore, there's no need to worry about the Markovnikov rule in this type of addition reactions. So basically what you have is a simple alkene reacting with a halogen like chlorine or bromine, and both the sp2 hybridized carbons will end up with a halogen each. So let's take a sample example. Let's take a sample example right here. So in here I have, let's say, propene. Here is propene, and I'm reacting this propene with let's say bromine, and then what happens is that I will get rid of the double bond first. You will get rid of the double bond, and instead the two carbons that share the double bond will get a halogen each. Very straightforward and a simple reaction. Okay, so alkenes will get rid of the double bond and then will attach a halogen to the sp2 hybridized carbons. Okay, so no need to worry about the Markovnikov rule. If you don't remember Markovnikov rule, according to Markovnikov rule, basically the hydrogens are going to go to the rich carbon, or the carbon with more hydrogens, and the remaining nucleophile is going to attach to the poor carbon, which means the carbon with less hydrogens. Once again, this is according to Markovnikov rule, but that rule is not important for halogenation reaction. Okay, this reaction is not important. This concept, Markovnikov rule, is not important for halogenation reactions. So let's go to the next slide. And in this slide, I have an interesting example. I have a cyclic alkene. The thing about cyclic compounds is that, because of the ring structure, they don't have free rotation around the single bonds. Because of that, alkenes could have a top plane and a bottom plane. You have a top plane and then you have a bottom plane. Because of this two planes, the atoms or group of atoms that you have on the top plane has a difficulty reaching to the bottom plane. So you have the cis-trans isomerism, and we discussed about these details in a previous lecture. But if you use a cyclic alkene, okay, you can expect two different products. Okay, the two bromines could be on opposite planes, or the two bromines could be on the same plane. If the two bromines are on opposite planes, we call it trans. If the two bromines are on the same plane, we call it cis. So we discussed about this cis and trans isomerism for cyclo compounds. But the significant thing about this cis trans isomerism is that when you try to halogenate alkenes, or when you try to do halogenation on alkenes, you only see the trans product. Okay, you almost never see the cis product. So basically, you only see the trans product. So we say that this reaction occurs with anti-stereochemistry. Because of that, we say that this reaction occurs with anti-stereochemistry. And this is a very unique thing about these halogenation reactions. Once again, you don't have to worry about Markovnikov rule, but now you have to worry about the anti-stereochemistry, especially if you have cyclic alkenes. So if you have cyclic alkenes, you tend to see the trans product over cis product. So in order to understand this phenomena, okay, we have to actually worry about the mechanism of this reaction. We have to worry about the mechanism of halogenation reactions. So this mechanism of halogenation happens through a bromonium ion. If you recall the electrophilic addition reaction of alkenes, usually it happens through a carbocation. But the halogenation happens through a bromonium ion. What is a bromonium ion? Bromonium ion actually has a cation on a bromine. That is the unique thing about bromonium ion. You have a three-member ring structure between a bromine and the previously sp2 hybridized carbons, and the bromine atom has a positive charge. So this bromonium ion tend to shield one side of the ring. So when you're halogenating alkenes, the previously electrophilic bromine can block one side of the ring, so that the incoming bromide ion can only reach the ring from the opposite side. So it can only reach the ring from the opposite side. So therefore, the product will have the two bromines on opposite sides. And that is why we say that it has an anti-stereochemistry. So that is a new thing that we just learned. Okay, that is a new thing that we just learned. And especially when we worry about halogenation of cyclic alkenes, we have to keep anti-stereochemistry in our head. All right, so as I mentioned earlier, this mechanism goes through the bromonium ion, which basically blocks one side of the ring. And this bromonium ion was postulated more than 75 years ago. But I mean, George Olga, the scientist called George Ola, was able to isolate this bromonium ion in liquid sulfur dioxide. So this is how bromonium ions looks like. All right. So let's talk about this worked example. So if you are watching this video, I want you to pause the video now and then see if you could do this worked example by yourself. All right. So in this worked example, what we have is HCl reaction with 1,2-dimethyl cyclohexene. So this is an electrophilic addition reaction between HCl and a cycloalkene. So let's first draw the cyclohexene. Okay, so here is my cyclohexene. Okay, and it has 2 methyl groups. Perfect. And then we are reacting that with HCl. So what you have is HCl. All right, so basically what happens is that we will get rid of the double bond, of course, and then first the hydrogen will be attached to the ring. Okay, so let's do this. So here is our hydrogen on this carbon. Okay, here's the hydrogen, here's the CH3 group. And you know this carbon also has a CH3 group, and then it has a carbocation. And then we also have chloride ions in the medium, and carbocation is an open cation, which means you know both the top side and the bottom side is open, so chloride can attack either from the top or the bottom, giving you two different isomers. So that is how it happens. That is why you get two different products for the addition reaction of HCl to 1,2-dimethyl cyclohexene. 1,2-dimethyl cyclohexene. So here is the answer. It is basically the same thing that I just mentioned. Once again, guys, the carbocation that we get here is unlike the bromonium ion. It is unlike the bromonium ion, and then it is not blocking one of the sides. So the chlorine could either reach from the bottom or it could reach from the top, giving you two different isomers. All right. So here is some more details about the solution, and I think I already explained all the details, but if you want you can pause the video and read the solution for more details. All right, so the second reaction that we are going to talk about in this video is called Halohydrin formation using alkenes. Okay, so if someone asks me what is a halohydrin, so halohydrin basically has a halogen and OH, okay, on the two adjacent carbons. Okay, so halohydrin has a halogen and an OH group, okay, on two adjacent carbons. So this reaction is very I wouldn't say very similar. It is somewhat similar to the halogenation reaction. Why? Because you are going to use a halogen like chlorine or bromine in this case. But the unique thing about this reaction is actually water. In previous halogenation reactions, we used dry bromine or chlorine, right? But in here, we are using water in our reagent. Because of this water, it provides a nucleophilic water molecule to the medium, which is basically responsible for the OH group that is going to be attached to one of the two sp2 hybridized carbons. That is the significant thing about this reaction. So the mechanism is very similar. To the previous case. Okay, and it will go through a bromonium ion. So right here you have the bromonium ion. Okay, so the mechanism is very similar, so it will block one side of the reagent. So if there is a bromonium ion formation, you might have to worry about anti-stereochemistry. Okay, so keep that in mind. So the mechanism will go through the bromonium ion. Okay, and then once the bromonium ion is formed, the water molecule will act as a nucleophile and then produce an OH group on the other remaining sp2 hybridized carbon. Okay, so that is how the mechanism goes. This is directly from your textbook. And here is a sample example for the halohydrin formation. In here, the reagents that I have used or your textbook has used is NBS and water. NBS is actually your bromine source. So this is what adds bromine to your medium, and then water is also there. And then let's see why you need NBr. Okay, remember in this reaction we need a halogen as an electrophile. Okay, so NBS gives you a bromine as a electrophile. Why? Because you know nitrogen is more electronegative. Okay, so it is going to be partially negative, and then bromine electronegativity is less as compared to nitrogen, so this is going to be partially positive. So this right here is your electrophilic bromine. This right here is your electrophilic bromine. That is important for this reaction. That is important for this reaction. And water gives you the OH. And if you take a look at this starting material, okay, so the two carbons are different. Why? Because at least when you take a look at the number of hydrogens you have on each carbon, these two carbons are different. This carbon right here has two hydrogens, 1 and 2. The other carbon only has one hydrogen. So basically, we can say that the carbon to the right hand side is rich. Why? Because you have more hydrogens. Hydrogens is like money. When you have more hydrogens, you are rich. You have more money. Okay, so that is the argument. Okay, at least for us. And then this carbon is your poor carbon. Here's the rich carbon and the poor carbon. Okay, rich carbon and the poor carbon. And then according to Markovnikov rule, hydrogen tends to go to the rich carbon. Hydrogen tends to go to the rich carbon. Am I correct? Yes. So according to Markovnikov rule, hydrogen tends to go to the rich carbon. So the remaining nucleophile will go to the poor carbon. Okay, so that is what we learned. Let me erase all of these. So basically, here is your rich carbon. Here is your poor carbon. So according to Markovnikov rule, hydrogen or your electrophile goes to the rich carbon. So in this case, our electrophile is the bromine. Okay, so bromine goes to the rich carbon. Okay, and then the OH, the nucleophile, goes to the poor carbon, just like Markovnikov rule. So this reaction behaves according to Markovnikov rule. This reaction behaves according to Markovnikov rule. Even though we don't have hydrogens, our electrophile goes to the rich carbon. Our electrophile goes to the rich carbon. So this reaction acts according to Markovnikov rule. And let's see if you could do this worked example without my help. Okay, so what you have is a cyclopentene. Okay, what you have is cyclopentene, and you are reacting it with NBS and water. So this is halohydrin formation based on the reagents, right? So pause the video now and see if you could do this worked example. All right, so in here, in this example, we don't have to worry about Markovnikov rule. We don't have to worry about Markovnikov rule. Why? Because there is no rich carbon, no poor carbon. There is no rich carbon, no poor carbon. But the alkene that we have is a cyclic alkene. So we may have to worry about anti-stereochemistry. Remember, this mechanism also goes through a bromonium cation, right? Bromonium ion. So because of that, we might have to worry about the anti-stereochemistry. And in fact, we do. And we don't worry about which carbon gets the bromine and which carbon gets the OH, but instead we have to worry about the orientation of the two incoming groups. So the OH group will be on one plane and the bromine will be on the opposite plane. Why? Because the products that you get from this reaction has to have anti-stereochemistry. How do you display anti-stereochemistry? You can easily use a wedge and dash. All right, so that is how you do it. This is the answer, but of course I'm pretty sure you already know that answer. Okay, all you need to do is to make sure that you display the OH group and the bromine group on anti stereochemistry on opposite planes. All right. So OH and Br are trans to each other because of the anti-stereochemistry. All right, so then in the next video, we are going to talk about hydration of alkenes. But with that, I'm going to conclude this video. I'll see you in the next video.